For nearly 3 decades, the cosmological constant has stood as one of modern physics' most perplexing enigmas. This mathematical term, originally introduced by Einstein and later abandoned, was resurrected in the late 1990s to explain one of the most shocking discoveries in the history of science: the accelerating expansion of the universe. What began as a convenient theoretical placeholder has since become the foundation of our standard model of cosmology, known as LCDM. But now, a series of groundbreaking observations from the Dark Energy Spectroscopic Instrument DESI collaboration suggests this entire framework may be on the verge of collapse, potentially heralding the most significant paradigm shift in cosmology since the discovery of cosmic acceleration itself. The story of dark energy begins with what should have been a straightforward measurement. In the 1990s, 2 independent teams of astronomers set out to measure how much the expansion of the universe was slowing down due to gravity's relentless pull. By studying type Ia supernovae, the brilliant explosions of white dwarf stars that serve as cosmic mile markers, they expected to confirm the gradual deceleration that had been predicted for decades. Instead, they found the opposite. The universe wasn't slowing down at all, it was speeding up. This completely unexpected result, which earned its discoverers the 2011 Nobel Prize in Physics, could only be explained by invoking some mysterious repulsive force that counteracts gravity on the largest scales. Enter the cosmological constant, denoted by the Greek letter L. This term, which Einstein had originally inserted into his equations of general relativity to maintain a static universe, before Hubble's discovery of cosmic expansion, suddenly found new life as the simplest possible explanation for dark energy. In this interpretation, dark energy represents a constant energy density, inherent to the fabric of space itself, a kind of background hum of the universe that never diminishes, even as space expands. When combined with cold dark matter, the CDM and LCDM, this model provided an astonishingly good fit to virtually all cosmological observations, from the cosmic microwave background to the large-scale distribution of galaxies. But beneath this apparent success lurked profound theoretical problems. Quantum field theory predicts a cosmological constant that is some 120 orders of magnitude larger than what we observe, the worst mismatch between theory and experiment in the history of science. This cosmological constant problem has been described by many physicists as the most embarrassing unsolved mystery in fundamental physics. For years, the community consoled itself with the thought that at least the LCDM model worked phenomenologically, even if we didn't understand why. Now even that consolation may be slipping away. The latest results from DESI, a state-of-the-art spectroscopic survey instrument mounted on the Mayall telescope at Kitt Peak National Observatory, suggest that dark energy may not be constant after all. By combining measurements of baryon acoustic oscillations, BAO, fossilized sound waves from the early universe that serve as a cosmic yardstick, with supernova data and cosmic microwave background observations, the DESI collaboration has found evidence at the 4.2 UZ level that dark energy's strength may be changing over time. The implications of this result are difficult to overstate. If confirmed, it would mean that the vacuum energy interpretation of dark energy is fundamentally flawed. Instead of being a constant property of space, dark energy might be something far more exotic. Perhaps a dynamical field that evolves over cosmic time, similar to the inflaton field thought to have powered the Big Bang. Or evidence that Einstein's theory of gravity needs modification on the largest scales. Or even a sign that our universe is but one bubble in a vast multiverse. The DESI instrument itself represents a marvel of modern astronomical engineering. Its robotic positioner can reconfigure 5,000 optical fibers in just 2 minutes, allowing it to capture the spectra of millions of galaxies across 1/3 of the sky. By precisely measuring the redshifts of these galaxies and mapping their 3-dimensional distribution, DESI can track how the BAO scale, imprinted when the universe was just 380,000 years old, has stretched over cosmic time. When combined with distance measurements from type Ia supernovae and the initial conditions set by the cosmic microwave background, this provides an extraordinarily powerful test of cosmological models. What makes the current situation particularly exciting is the convergence of multiple independent lines of evidence suggesting problems with LCDM. The so-called Hubble tension, a growing discrepancy between different methods of measuring the current expansion rate of the universe, has been worrying cosmologists for years. Now, with DESI's suggestion of evolving dark energy, we may be seeing the emergence of a coherent pattern of anomalies that can no longer be dismissed as mere statistical flukes or systematic errors. The coming decade promises to be transformative for cosmology. The European Space Agency's Euclid mission, launched in 2023, is currently mapping billions of galaxies to measure cosmic structure growth and weak gravitational lensing with unprecedented precision. The Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, set to begin operations soon, will discover hundreds of thousands of lensed quasars and millions of supernovae, providing multiple independent constraints on cosmic expansion history. Meanwhile, DESI continues to collect data, with its full 5-year survey expected to either confirm or refute the evolving dark energy signal beyond any reasonable doubt. As we stand on the precipice of what may be a scientific revolution, it's worth reflecting on how rare such moments are in the history of science. The potential overthrow of LCDM would represent the most significant shift in our understanding of the cosmos since the discovery of cosmic acceleration itself. It reminds us that science at its best is not about defending established dogmas, but about following the evidence wherever it leads, even when that evidence points toward conclusions far stranger than we ever imagined. The universe, it seems, still has the capacity to surprise us. Whether DESI's anomalous results ultimately hold up or not, one thing is certain. We are living through an extraordinary period of cosmological discovery, where the fundamental nature of reality is being probed with ever-increasing precision. The answers we find may well redefine our place in the cosmos and force us to confront profound new mysteries about the nature of space, time, and existence itself. Join us as we continue to unravel the universe's deepest secrets. Like, share, and subscribe to stay updated on humanity's greatest adventure, the quest to understand the cosmos and our place within it.